Hello everyone, my name is Tang, a PhD student from Pennsylvania State University. My advisor is Dr. Shanbiao Hu. Today I'd like to share the topic about identification of operational design domain for autonomous truck-mounted attenuator system on Multilane highways. As we know, the mobile and slow-moving operations are critical for the efficient and safe operation of a highway transportation system. Performing the maintenance required for a roadway infrastructure, however, could involve risks, and many of work zone crashes involved state DOT workers. The autonomous truck-mounted attenuator named ATMA vehicle combines the use of CAV and AMT, which is in leader and follower system, to remove the DOT workers from the following trucks. However, the guidance for its deployment is largely missing in the MUTCD and other federal regulations and national standards. When and where to deploy the ATMA, how to evaluate the impact of ATMA vehicles on Multilane highways traffic flow, how to identify the ODD on Multilane highways. Here we select the AADT as our ODD for the ATMA system. If ATMA vehicles performs maintenance on a 4-lane highway segment, it will become a moving bottleneck due to slower speed. It leads to capacity drops or discharge rate discounted. We need to analytical derive at first. Then the delay and density can also be derived to determine the level of service. Based on that, we can get the ODD or AADT of the ATMA system. This figure describes how speed and density determine level of service and different free flow speed for Multilane highways. Under normal traffic condition, we apply Newell's car-following model, which suggests a triangular fundamental diagram. From this figure, we can derive the discharge rate mu using this equation, and then we focus on a typical highway with 2 lanes of the same direction. As the ATMA vehicles enter this segment, how does the discharge rate change? And it becomes a moving bottleneck from a moving observer's view with the same speed with ATMA vehicles. The 2 lane will drop to 1 lane. In this figure, this black triangle is from a stationary observer's view, and this red one is from a moving observer's view. What we need to derive is the H prime and M prime, which is the effective discharge rate. After that, we can calculate the Q, delay, and density. Thus, we derive the level of service. In numerical analysis, we first validate the effective discharge rate using the NGSIM data from IAT, and we can find that the absolute percentage L of effective discharge rate are obviously lower than that of maximum discharge rate. Under a typical scenario with characteristics listed here, we can find that when the AADT is lower than 45,000, there is no delay. And when the AADT goes up, the delay will increase from 0 to 36 seconds. And about the density, it increased from 9 to 24 vehicle per mile per lane when the AADT is less or equal to 40,000. So if our desirable design objective is level of service C, then our ODD will be the AADT is no more than 40,000. And we also perform the sensitivity analysis to see how does it change when the K factor, D factor, and the operating speed of ATMA changes. We can find that the AIGT threshold will change corresponding to. Thank you.